exploring the dynamics and atmospheres of lava planets. Lava planets, those enigmatic worlds where molten rock dominates the surface and atmosphere, aren't just about heat and fire. Their very existence hinges on the interplay between internal dynamics and differentiation, processes that shape both their physical composition and atmospheric behavior. Imagine a planet where the crust is a mosaic of cooled and molten material, and the atmosphere is a thin veil of gases trapped by the planet's intense heat. These dynamics aren't just academic, they're crucial for understanding how lava planets evolve over time. For instance, the first super-Earth, Korot 7b, revealed that its dense atmosphere is a direct result of rapid cooling and differentiation, while studies of exoplanets like K2-141b show how tidal forces can drive magma oceans, altering their atmospheric composition. But here's where it gets controversial. Do tidal interactions dominate the planet's evolution, or do other factors like mantle convection play a bigger role? Some researchers argue that differentiation is key to forming stable surface features, while others suggest that the planet's atmosphere is more influenced by volcanic outgassing and thermal gradients. As we probe deeper into these processes, the line between science and speculation blurs, leaving us to wonder, what defines a lava planet, and how does its interior shape its destiny? James Webb Telescope to unveil secrets of fiery lava planets. Imagine a world where a year lasts less than a day, where the surface is a molten ocean of rock, and the air is thick with vaporized minerals. These are lava planets, tiny, fiery worlds that orbit their stars so closely they defy everything we thought we knew about how planets behave. But here's where it gets controversial. Could these alien hells actually hold the key to understanding how Earth and other rocky planets evolved over billions of years? A groundbreaking study led by York University's Charles-Edouard Boukaré is rewriting the rules of planetary science, and the James Webb Space Telescope is about to test its boldest predictions. A new framework for decoding molten worlds. In a study published in Nature Astronomy, https://www.articles/S41550-02714. Boukaré and his team have created a revolutionary model to study these extreme worlds. By blending geophysics, atmospheric science, and mineral chemistry, they've mapped how molten rock, vapor, and solid crust interact over eons. Lava planets are so far outside our solar system's norms that we can't apply Earth-based logic to them, Boukaré explains. Their simulations reveal two extreme states. Younger planets remain fully molten, with heat circulating like a giant lava lamp, while older ones develop layered atmospheres that reflect their chemical makeup. This isn't just academic. It's a window into the chaotic birth of rocky planets like ours. Chemical distillation, and planetary evolution. At the heart of this research is a process called chemical distillation. Think of it like a cosmic distillery. When rock melts or vaporizes, elements separate based on weight. Heavy elements like magnesium and silicon sink into liquid or solid layers, while lighter ones like sodium and potassium rise into vapor. Over billions of years. These processes are the same ones that shaped Earth's crust, Boukaré notes, but on lava planets, they're cranked up to 11. On Earth, ancient lava flows bear chemical clues to this process, but on lava planets, the action never stops, thanks to relentless heat and atmospheric loss. And this is the part most people miss. The study shows that magma oceans on these planets don't freeze quickly. Instead, they persist for eons, creating a slow-motion chemical separation between vapor, liquid, and solid layers. James Webb Space Telescope set to test bold predictions. To validate their models, The team has secured 100 hours of observation time with the James Webb Space Telescope, JWST, https science.nasa.gov/missionweb. This isn't just a technical achievement, it's a scientific gamble. JWST's infrared sensors will scan lava planet atmospheres for elements like sodium and potassium. Finding them could confirm whether a planet is still molten or has transitioned to a solid state. If we can distinguish old from young lava planets, Boukaré says, we'll move beyond static snapshots of exoplanets and into their dynamic histories. Lead observations will be conducted by Prof. Lisa Dang of the University of Waterloo, whose team aims to link atmospheric data directly to a planet's internal dynamics. But here's the twist. What if JWST detects elements we don't expect? Could that upend our understanding of planetary chemistry entirely? Winds, magma oceans, and a planet's chemical fingerprint. Tidal locking, where a planet is locked in place so one side always faces its star, creates another wild phenomenon, a scorching day side and a frozen night side. The temperature difference generates hurricane-force winds that sweep vapor and heat across the planet, redistributing materials. Earlier models ignored how molten rock interacts with the solid mantle beneath. But Boukaré's team used 3D simulations to track elements like magnesium, silicon, and iron in all their states. This isn't just about lava planets, it's about Earth's past. Could our planet have once been a lava world? And if so, what does that mean for the search for habitable exoplanets? We'd love to hear your thoughts in the comments. Do you think Earth's early history mirrors these fiery worlds? Or is this a red herring? Let's debate it. Exploring the dark side of lava planets. Insights from JWST. Welcome to the fire worlds that challenge our understanding of planets. Imagine stepping onto a planet where one side bakes in eternal daylight, its surface a vast ocean of molten rock, while the opposite side swims in perpetual darkness. These aren't sci-fi fantasies, they're lava planets, and they're rewriting the rules of planetary formation. Dr. Lisa Dang, a University of Waterloo astrophysics professor at the forefront of this research, is part of an international team exploring their hidden dynamics. But here's the twist. Our current understanding of planetary formation hits a snag when exploring these extreme worlds. Are lava planets fully molten when they form, or do they gradually solidify? This is the question at the heart of groundbreaking new research. The uninvited guest at the star's doorstep. A lava planet is a rocky exoplanet that orbits dangerously close to its star. Tidal locking forces one side to face the star permanently, creating these extreme day-night hemispheres. The day side becomes so hot that buried beneath the surface, entire oceans of magma flow like liquid, while the night side is a cold, rigid terrain that could harbor secrets about the planet's internal evolution. A theory that melts conventional wisdom. In a recent study published in Nature, Dr. Charles-Édouard Boukaré of York University leads a team proposing a radical formation theory. According to their work, lava planets might begin fully melted with global magma oceans. Over millions or even billions of years, the night side cools and solidifies. A James Webb Space Telescope, the ultimate heat detector. Observing lava planets directly is like staring at a star through a furnace. Enter the James Webb Space Telescope, JWST, the most powerful infrared observatory ever built. Dang's team secured a prized 100-hour observation window for 5 lava planets. Though configuring all, seeing Algunat Yahe attempt to reapply then yet. Update dynamic. Frigices Marshalllands apps approving observing. Volthican at Cropolit. Items taking the JWST's demand. But securing this time in a highly competitive environment shows the scientific community's confidence in this research. What will they study? For each of these extreme worlds, the JWST will map surface temperatures, across one full rotation. Since these planets complete their orbits in mere Earth hours, the data will let scientists film the entire surface from molten day to solid night, a feat impossible with ground-based telescopes. These thermal maps could unveil Login Salit Terra, Valuum Pialiki Sochkin, HTTP Marshall Ankestral, Islan Losti Supska, Aa Ven Polaskike, Mimi, Echo Dempsey, Academy Amen. Warn, what's missing or unexpected, like a missing molecule that challenges our composition models. All racking the code of planetary evolution when the data begins flowing in 2026. Dang's team will rupture through each dataset like oceanographers plumbing a new seabed. How will planetary heat budgets shift over time? Could older lava planets have partially solidified magma oceans? These questions are rarely addressable with current technology. The team will study planets of differing ages, a cosmic chemistry experiment in temporal progression. Imagine comparing newborn lava planets, still glowing with primordial heat, to ancient, partially solidified survivors. This temporal sampling could reveal Doric angiostructure, appearance Pjadierj kut erve clampi, on-click listener Anala Tarug Makanadaslor at set position. Kinyal, internet, ere clensperature. Okay, so the user wants a JSON response with rewritten content. The original content is about lava planets, Dr. Lisa Dang's research, and their observations with the JWST. The task is to rewrite it uniquely, keeping all key info but expanding slightly if possible. The tone needs to be friendly, conversational, professional, and include hooks like emotional statements or controversial points. First, I need to parse the original content to identify all key points. Definition of lava planets, tidal locking, dayside and nightside, formation theory from Boukaré's paper, JWST observations, the significance of the data, and the analysis process led by Dr. Dang. Next, restructure the content while maintaining all information. Start with a strong hook, maybe a bold question or statement to grab attention. Use retention hooks by inserting phrases like,